don't. Thank you, Ali Reza. I just went through and see, I was just talking about the stream being set up the correct way. Uh, see, Ali Reza is one of the great guys on this channel. He takes care of me. uh, yeah, so go through all of that again. Welcome to the stream. Just trying to get everything set up. It's been a long week already. Normally these live streams are on Monday, and I've had 2 Mondays already. The first Monday, second Monday, and now we are on the 3rd Monday. So yes, welcome to the stream. This is your first time on. My name is Jason Watts. I am the founder and CEO of a little automation company called Alpha Industrial Technologies out of the southern US. I've got about a little over 20 years of experience working with Siemens automation technology, a lot of drives experience. But today we are going to be talking about some PLC topics. We're going to be talking about some, what do we call it? Some puts and gets, some offsets, data blocks. So if you didn't know, we have a Discord channel, or a Discord server that you are welcome to join in. It's a public server where we kind of talk about different things. There's a help desk portion of it to where you can come and ask your questions, and anybody is available to come in and do that. And we've got a good community of everyone going through and helping each other out. And so the past couple weeks I've been on some startups, and we've had some topics that have come up, and we've talked about them on Discord, but I think there's a lot of things that's come up, and it's like, hey, it's better to talk about it in person and kind of show it and kind of go through. So we're going to go through some of those topics today. So yeah, if this is your first time on stream, welcome to the stream. Be sure to like it and look through the channel as well. If this type of content suits you, try to do these streams at least once a week. We've got some pretty cool topics that are coming up that I have written down in my notebook here. And yeah, today we're doing another help desk, trying to clean up some questions and everything. Got a couple of different things, but some of the stuff that we are kind of brought up that I would like to talk about. One of them is doing our second motion control class. A few weeks back we did a motion 101 class, and we talked about kind of the general ideas of motion control, and I've got some things for what I would call motion 102, kind of the next level of that, integrating multiple motion functions into one system. And yeah, the next thing that I would really love to talk about is functional safety standards. And I know that sounds like kind of a boring topic, but there's a couple of different standards that if you're looking to get the CE mark on your equipment, that it is really good idea to understand how to kind of design for these things going into your system. But those systems are also, the functional safety standards are coming into the US a lot more as well. And yeah, it's a very good way of kind of designing your system with the thought of safety up front. So probably the next stream we may be doing that. And then I just went through a INDIRECT class 2 weeks ago, and INDIRECT is stinking awesome. And I kind of want to do a little bit of an introductory class to INDIRECT, because if you're in the CNC world and you're kind of used to the G code and cutting metal and all that stuff, INDIRECT just makes sense to you. Whereas if you're coming from the PLC side, I don't know, like for me, I knew kind of what it did. I knew how it kind of controlled stuff, but I didn't really understand the deep down things on it. So we'll be doing a stream here coming up soon about INDIRECT as well, probably in a couple weeks. But yeah, all of that stuff, if you are interested in that sort of stuff, yeah, be sure to at least subscribe to the channel. One thing before we really get started on this is all of the topics that we'll be talking about today. I'll probably be making some PLC data types, making a couple of functions, and those functions and most of the things that we go through, I it will be made available to the members in different member levels. So if you're interested in supporting this channel a little bit further, um, um, if you are interested in supporting this channel further, you can join in memberships and you get access to a Google Drive that gives gives you the ability to yeah to have the files and things that we go on stream. Now today I'm going to be using some files that I will not be making the full project available, because they are actually customer projects, because I wanted to show you kind of real code that is actually working and actually running on some equipment and different plants and factories. So can't make those available, but I can make some of the data types and those things available. So try to make it worth it for our members. But yeah, so yes. And welcome to the stream, Ignatius and Alireza. As you come in, be sure to drop a hey in the chat so you can distract me. I never get distracted on these. And yeah, so Alireza's like, so the thing about it, Ali, Siemens does have a G-code on the PLC for the technology objects. For the kinematics, they actually do have a G-code compiler for it. I haven't used it, but there actually is a G-code compiler available for the technology objects. So yes, happy Alpha Industrial Technologies Week. Yes, like that. That's every week for me, because that's my baby. My company is my baby. Yeah, and kind of literally, because I don't have kids. I have a company. But yeah, let's get going and talking about what we are going to be talking about today. And just kind of a side note, as I get everything pulled up, I have enabled ads on this stream, and this might be the first time that you are seeing some of the ad breaks, and give me some feedback on that, because honestly, I have YouTube Premium, and so I don't know how the user experience is on these live streams with ads. And so if you don't have YouTube Premium and you're getting ad breaks, just drop in the chat, say, hey, I just had an ad break. And just so I'm aware of how that affects it, because honestly, I may turn them off while live. And so I may do that in the future. So if you haven't put in the chat, just say that. Yeah, so today we are going to be talking about some things that have been in the help desk. Been working with a couple guys in the help desk about working with some kind of secondary data types. Well, it's not really data. Well, it's kind of custom data types, but it's a concept that there is a. Let me bring up my other sketch pad up here, like that, and wanted to kind of go through, and there's a concept of in the sensor world called HART, H-A-R-T. And if you have, say, like a pressure transducer or a flow meter or something that has some sort of analog value that's feeding back into your PLC, say this is a 4 to 20 milliamp signal. Okay, we're kind of aware that's probably going to come back on 2 wires, and it's going to be an analog signal, and so it's going to come in here into an AI, and so it's going to come into an analog input. Well, if you're not familiar with what HART protocol is about, is it actually puts a digital signal onto your analog signal so that the sensor itself can communicate more than just that analog value. And so it kind of puts out onto this analog signal. That's a terrible digital signal, and actually communicates digitally back to the analog input card. So it's a way that you could get more than just pressure or flow or temperature. You can get all these other variables out of these sensors, because normally a sensor, a single sensor package has a lot of information on it, such as temperature and pressure and like all sorts of stuff on it. So this conversation, we're going to talk about using the block read record. And what that is a data record. Okay. And honestly, in order to use the HART protocol, you are needing to use this concept of data records. And we're going to get to this concept towards the end. So I'm kind of talking about where we're going to get, but we really need to talk a little bit at first about how to organize your data. Because the user that is in Discord, the thing that's kind of tripping him up is how the data is being organized once you use this read record data block or read record function block. So let's go through and we'll work our way to it, but we're going to start first at kind of a concept of basic data structures. And the way that I'm going to do that and kind of show that is through the concept of, we're going to use a thing called put and get. It is a function block that is a little bit easier to understand than the read record at first, because a put and a get uses the same thought process, but it's communicating out to a sensor over a communication path. In this case, we're going to be over Profinet. And so I'm going to show you a project that I've actually been working on that uses puts and gets to communicate between two, it's actually 6 S7 1200s, and to communicate kind of across a pump system. So I'm going to bring up this, and I'm going to hang out in the bottom right down here, because what I want to show you guys is a little bit of a concept. Actually, before we get started on this, let's talk about data types real quick. I wanted to talk about that. I got a little bit ahead of myself before we actually get into Portal. Let's go back down to the sketchpad down here. So when you use data types, I talk about data types, custom data types, all the time. And in Siemens, in Portal, those are called the PLC data types. Sometimes you'll see them called UDTs, and in other languages, they will be called structures. And so it's kind of a little bit of a way to organize your data so that you can have you can bring in one kind of structure, and it gives you all sorts of bits and bytes and real values and integers. And that's kind of the higher level version of your basic data types. Okay. And that's what we're going to talk about here, are the basic data types, because if you have never worked with kind of an embedded controller or an embedded PLC, not a PLC, but like a microcontroller, like an Arduino, something like that, you may have just skipped over kind of the having to use this, especially if you're working with or if your experience is coming from like Allen Bradley, to where everything is tag based. And so like in an Allen Bradley processor, if you set something up as a Boolean, you know that's going to be true or false, but it takes up 32 bits of data. in the processor because it's a tag. And then there's just a tag property that says that, hey, this is a Boolean. Well, in Siemens, that is not necessarily the case. And honestly, a lot of different things. So this is a concept that's not just for PLCs. It's for memory architecture, for normal PC architecture, for artificial intelligence, like anything that's using hardware level processing. You're going to be having to deal with these concepts of different types and having different memory sizes. So let's get going on this. Which, by the way, I brought out the Siemens swag. That's how you know that like I'm completely like on board with Siemens. I haven't gotten a Siemens tattoo yet, but I don't know. Maybe if they sponsored this channel, I might get a Siemens tattoo. Probably not. My wife would. She already doesn't like my tattoo anyway. So that would cause strain. But getting distracted. First time this stream. We need to have like a count of how many times I get distracted. So let's go over just some of the basic types. Let's talk about like a Boolean, for example. A Boolean. We know that we'll say this is the type and this is kind of like what it is. So a Boolean is either going to be a 1 or a 0 or a true or a false. And again, if you've been using PLCs and processors and things like this is definitely going to be a basic review. We're going to start at the bottom, work our way up so that hopefully you fully understand the concepts of what we're doing here. So that's a 0 or a 1, a true or a false, and it takes up, we'll say this is the size over here, and it takes up 1 bit. Okay, so that is on or off. That's one transistor can store 1 bit. That's the basis of all thing is 1 bit, and that's a Boolean, on or off. Well, the next size up technically is a nibble, but the next size up that we normally use is what's called a byte, B-Y-T-E. And you're probably familiar with this, even if you're not aware of it. I mean, but kilobyte, KB, megabyte, gigabyte, that's byte. Like that's what we're talking about here. And it can hold a number in decimal from 0 to 255. Well, I guess technically it's n minus 1, so it's 254. But so it can hold 255 states. So that's where we kind of get binary number representation. And technically this is 254. But so it's a collection of bytes. And so it is actually, or sorry, collection of bits. This is actually 8 bits. So every byte has 8 bits. Pretty basic, you probably know that. Cool thing about a byte is because it is 8 bits, that number can be represented by 2 hex places. So hexadecimal is a number representation, which kind of talked about this before in other streams, but it's represented with a 0x, and then each place can have 16 0 through 6 or 0 through 15, so it can have represent 16 numbers. So this is where you can get like 0F3 or something like that, and you'll see this a lot in memory structures and things. So 1 byte can be represented by 2 hexadecimal numbers. So you'll see this a lot. And I said a minute ago, and it sounds like a joke, but half a byte is a nibble. And what a nibble is, and nobody ever really uses a nibble, but is just 1 hexadecimal number. So half a byte is a nibble. I mean, you know, you're not taking a full byte, you're just taking a nibble. Yeah, engineers are, oh, we're so funny. Oh, everyone. So, up from there, we get what is called a word. And it gets a little bit different because normally a word is going to be the smallest addressable space. And so on a Siemens PLC, a word is 2 bytes, so 16 bits. So a word can represent, it's just a collection of 16 bytes. Some architectures, some processors, their word is a 32-bit word. And so, but in Siemens land, 16 bits. So a word is going to be 0 through, and these numbers are 0 through 2 to the 15. That's going to be the numbers that it can represent. And so, it's like 64,000 something. I don't know. It's a big number. And that's just in binary. That's the number that a word can hold. Okay, cool. We then have the word. Oh, let me put this. So this is 2 bytes. Okay, and we're going to start looking at this sort of thing because later on we're going to be talking about some offsets. We're going to be creating some pointers for these puts and gets and the read records and write records. You have to kind of understand offsets in data blocks, and that's why we're going through this. So a double word is, oh, I just slipped up. It's 2 words. It's double words. So you're looking at 0 through 2 to the 31. So very big. All right. Well, these are kind of the basics for, and this is going to be 4 bytes, 2 words. Okay. Now, these are all kind of like bits and bytes. So right now we haven't really said anything about integers, double integers, real values, floats, like anything like that. We haven't really talked about that because these basic structures, these are the basic sizes that we're going to be working with in our data blocks. So now let's talk about an integer. So an integer, we know, is plus or minus 32,000 something value. Okay, and that's because it is 16 bits, just like a word. So an integer is plus or minus 2 to the 14. So, sorry. And so, oh, that's 2 to the 15. No, 2 to the 14. Because you have 0 through 2 to the 14, and then 0 through 2 to the 14, and then plus or minus. So you have 1 bit, and so that's an integer. Well, this, because it is the same size as a word, it's going to be 2 bytes. So you can kind of move on from there. A dent or a double integer just has a bigger space to store bigger numbers, and so it takes up 4 bytes. Okay, fairly simple. And again, this is very much review, but it's very fundamental in understanding what we're going to be talking about later. Now, a real value is a little bit more complicated, and honestly, I'd have to go through and look at the definitions of how it calculates what the values and everything are. But these are going to be like 1.5. It's something that has a decimal place, so it has a whole portion, and then it has a decimal portion. Okay, and in order to store all that data, that number can get really big because there's like an exponent. So it can make that exponent really big. And so this real value actually takes up 4 bytes. Every real value takes up 4 bytes. Now, double int and real are the largest standard data types. So these basic data types are the largest standard data type. Now, I talked about it earlier about how Allen Bradley, if you have a tag, if you wanted to make a processor and make it to where I could have one tag that could store any data type, well, that tag would have to be 4 bytes big. So that's 32 bits. So that's 32 bits of information just to store any tag in Allen Bradley. Well, in Siemens, because it's not actually tag based, you can have 1 bit. You can actually use 1 bit, and I'll show you kind of like the memory architecture and things of how things are used in here in a second. But in a tag based, you have to be able to hold a real value, a double integer value, all of these different things. So you have to have those 4 bytes, and that's why these tags equals 32 bits. Now, what if you only use 1? Well, if you label a tag a Boolean, it's only a true or false, which is just on or off, but it still takes up 32 bits in memory. So that's not efficient. Which, by the way, that's why if you were looking to do like an Allen Bradley to Siemens conversion on something, and you're used to these really large program memories and really large workspace memories in order for your program, the thing about it is, if you have a lot of digital logic, just like on and off, that program in an Allen Bradley is going to be sometimes it could be up to 8 times the size, just because if you have 100% digital logic, no, sorry, 32, because 1 bit takes up 32. So every bit that you use is going to take up 32 times the data on an Allen Bradley processor than it does on a Siemens processor. Now, you can still process it probably just as fast, but just the size of the program just starts to balloon if you have a lot of Booleans. Now, if you don't have a lot of Booleans and you're doing a lot of like real math, the program sizes are probably going to be about the same. So if you're doing a lot of like evaluation of positioning and evaluation of set points of like analog signals and things like that, it's probably going to be about the same. But just don't be too shocked when if you're coming to these videos and coming to these things from the Allen Bradley world and saying, my goodness, like Siemens processors don't have any memory. I can't write this program because I need this much. Well, you'll find that your program size will be a lot smaller on a Siemens PLC. So that's kind of the concept that we need to talk about what we're going into kind of in this help desk topic, because the thing that we're about to talk about is how data is stored in a data block on a Siemens PLC. We've already talked about the difference between like an Allen Bradley PLC to a Siemens PLC. Now let's talk about, there's even a little bit of difference in the Siemens PLC itself. So let's go up here. Now just remember, let me do this and then come over here and go up to, want to be in bottom right. All right, so sorry, checking a couple of different things. What's up, OG? Another member in the chat. It's good to see you. Welcome to the stream. We love to see everybody coming in and love to see those blue stars. Hey, hey, Ollie, you know my view of Alan Bradley, and like it has its functionality and its place, and you have to give a company where they do, and do give their due where, I don't know, something. I got to be nice. That's what I'm trying to say. I've got to be nice because I am I am an American, and I use the German PLC a lot. So I want to show you a little bit about um, this structure. So what we have is a PLC system where we actually have six 1200 PLCs, a big drive, and this drive is a 250 kW drive, I believe. Drive, let's see what size this is. 200. So yeah, 200 kW. So this is on a pump system, and these stations, each one of these stations are miles apart in the middle of nowhere, Alabama. If you watch my stream, you will have, or watch my channel and shorts and things like that, you'll actually have seen this mine on one of my shorts here recently. But this is the project I was working on last week. And let's look at how these, I'm going to show you how these remote pump station data is kind of put together. Okay, actually, let me look at it from one of the remote stations, because it's a little bit different, and I'll explain why here in a second. So I'm going to look at one of the remote stations, station data. Okay. What we have is the master system data, which is the first station that's controlling all these pump systems. And the way that this data is organized is into a couple of different things. So you can see I have some reals, some integers, and I have a word down at the bottom. And then I have this custom data type that I've made called pump remote control. And in it has a bunch of Booleans. So this is the control word coming from the master. And so then down here at the local data, so this is going to be the status word. So all of the information according to the local station. So these local stations, you can go in and flip a switch, turn them into local control, set the set points, and run that 200 kW pump. You can just run it from there. Or you can flip it over into remote, and the main system 6-7 miles away is going to be controlling the flow. Well, same thing you could see here. I've got some reals, ints, all of that. All of the stuff that is coming back to the master system. And I wanted to show you one thing that's here. I have this column called offset. Okay. And this is going to be very important in using a put, a get, or a read record, or a write record, because this offset is required if you're going to be using these functions. And yeah, we'll talk about it here in a second. I don't know if this one, is this an optimized one? Yeah, so compare it to this data block. So this is an instance data block from my control function. That's the local control function block that I made. And if you notice, it does not have this, the offset. And so you're saying, okay, where is it? This is just a data block, technically. You're like, well, it's an instance data block. Yeah, it is. But the reason that there is no offset is because in the properties, and so I just right click properties and I go to attributes on that block. On the station data block, I have turned off optimize block access. That generates to where no matter what, it is going to take up a continuous block of memory, and it's going to have that offset. The reason you have that offset is because if you don't do that, optimize block access can, and sometimes does, put that in the actual memory. It puts it into different places in the actual memory, and all you're doing is just saying, hey, I've got a tag, I've got a symbolic address that I'm going to, and I'm not actually going to a physical place in memory. And it sounds like, okay, how is that different? I'm accessing it the same way. Yeah, you still have the tags, you still do data block, station data dot remote station data dot whatever, but the way it is actually stored on the PLC is fundamentally different. In an unoptimized block access, it takes up a full block of data. So if you don't have enough space to fit that unoptimized block into RAM, into your working memory, then it will jam it all the way down to the end and put it at the end. And so even if there's a lot up above it, then it's going to be having the same thing. Processor takes care of all that, but you have to have the optimized block access turned off to use put, get, read record, write record. So you know, that's okay. That's the difference. When you turn off optimized block access, you get this column. You get the offset column. And so what that is if you start up at the top of that, data block and you look at, remember we talked about how much data different data types take up? That is how many bytes down in the data block that offset is. And so you can look and see as we go through byte offsets, it's going here. Inside these Booleans, you'll see that they actually have bit offsets as well. Cool thing about it is this is all setting up what's called indirect addressing. And I did a video, a live stream about indirect addressing, but it's a pretty complex topic, honestly. But a lot of machinery, a lot of assembly lines use indirect addressing just so that you can kind of use recipes and use modular code. And yeah, there's just a lot of things that indirect addressing does. So that's what this offset is. Starts at the top, goes down the offset. So a .1 is 1 bit, a full is 1 byte, so 8 bits. So you can see I normally structure my control words to where I consume 16 bits anyway. I consume an entire word. That's why you see I have these spares here. And that's because I know that it's going to take up that space in memory anyway. I want to go ahead and make it available. And then that way I don't have to reinitialize this data block if I go in and change just the tag. So a little word of advice there. If you go through and you change in the data structure, like if you have a data block and you change this spare 4 to something that's actually something, you don't have to reinitialize that data block. So all your values don't go back to their start values. So that's why I do that. And if you're doing bits, go ahead, just use 16 bits and just make it and put in spares. That way your offset on your unoptimized data block will come out. The next one will just be 2, because most everything, integers are going to be integers, reals, those are all going to be multiples of 2. So, by the way, Ignatius, I'm so glad you've come to the world of Siemens. In the grand scheme of things, I mean, if you're doing work in the US, I'm kind of a glutton for punishment. To me, there's plenty of Allen Bradley programmers out there, and they do a really great job working with Allen Bradley. I want to work well with Siemens, and there's not as many of the Siemens programmers in the US. So if you're kind of wanting to get an edge in the market as an integrator or as a programmer, knowing Siemens is a very powerful tool in your tool belt. So as we talk about this, which So this offset we've talked about is based on what type of data is there. So let's kind of just take a real thorough process of going through and really understanding what this offset is. Because when we start talking about later on about this HART protocol, this is what we are going to really have to talk about and really understand, is because when you start using indirect addressing and things start coming in, this data type, it doesn't actually care about what that data type is. All it cares is where it's shoving that data. And we'll talk about that here in a second. So here we see that the real value starts at 2. So this supervisory drive speed set point starts at offset 2. So if we wanted to reference this with a pointer, it would be db1, because this is db1, dot dbd, so db double 2. And so that would be the start of that that offset, because it is a dbd. A real takes up 2 words, so db double word, and it is going to take up, so that's going to be 4 bytes. So it's going to say, you're going to start here, here's your pointer. That's how we would reference this offset, because it is dbd2. It's saying start at offset 2 and then go 4 bytes, and that's the reference for it. Now the next value will be 4 bytes away. So 2 to 3, 4, 5, 6. So it'll be at 6. So this is the start of the next value. And you can see how these real values, this value increments by 4 every time. And so the next value, even though this is an int, it's still incremented 4 because the previous data type was a real, which is 4 bytes long. Okay, so an integer is only 2 bytes long. That's why when you go from this offset to this offset, it's an integer, and so it's only 2 bytes. So system state, which is an integer, if we wanted to reference that value, it would be db1 dot dbw, because it's just one word. It's not a double word. It's one word. So dbw dot 14. So sorry, not dot. dbw 14. And then the next available pointer, the next available start would be word 16. Now we get kind of down here into the very bottom. An integer, I have this as a word. And so there's a subtle difference between a word and an integer. And it's really just the fact that you are defining what the data is. A word is just a collection of bits. Now, I could go and call this sequencing word an integer and use it exactly the same, especially the way that I'm doing it. But because I want to signify to anyone that comes behind me that this is not a number, that it is a collection of bits, I say that it is a data type word. Functionally, bits are bits. But so because what this sequencing word is I've taken 16 bits and gone through, and each one of these pumps has a location number. And so it will collect up into one word that will tell the running status of all of the pumps in this system up to 16 pumps. This one only has 6. We can expand this system up to 16 with this same structure. So if you notice, that word starts at 32, same thing as an integer. So the next available offset is going to be 2 bytes later, so 34. Now you say, okay, well, Jason, This is a totally different data. This is a totally different data type. This is like a totally different jump. Yeah. Remember, a custom data type, you can kind of think of it as a collection of standard or basic data types. And that's what we have here. My pump remote master data type, if I shrunk this all the way down, oops, not that far, you'll notice that it's actually 34 bytes long, because the next available byte address is 34. Okay. Same thing. A reel takes up 4. My custom UDT pump remote master data takes up 34 bytes. So that's going to be relevant here in a second, because we see here, and it's the same concept going down through, and I'm not going to go through, but you can look at these different offsets and these different data types. So when it's a reel, you go from 36 to 40 to 44 to 48. Then that's an integer, so 48 to 50. Then 50 to 52, that's a real, so 52 to 56. Same thing. So based on what the data type is, that determines how far you jump on your offset. So pretty basic stuff, but if you're not used to using memories and offset, and you're just used to using tags, then this might not make sense off the start, and nor should it, because you've never been exposed to it. That's why I kind of jokingly talk about on some other streams, like how I can tell if you're an Allen Bradley programmer when you're programming in TIA Portal, because of the way that some of these things, because most Allen Bradley only programmers are used to just creating a tag, and every tag is 32 bits. And so you never have to think about, oh, what is these offsets and things like that. So don't feel bad if this is something that you've been programming for a while and you're like, what the heck? Don't even understand what this is. So what we're going to go do now is I'm going to go back to this master pump system, because there is a OB30, which is a cyclic interrupt block. Hey Ignatius, I'm the more you use Siemens, the more that you are going to be somehow this one got broken, but for PH5, okay, all of a sudden it's fine now. Oh, I must have accidentally scrolled on that at some point. So this is PH5. Yeah, that's fine. So what we're doing in this. So if you're not familiar with kind of the difference between these purpley blocks over here, the green blocks, the blue blocks, OBs, FBs, FCs, DBs. If you're not familiar with the difference between those, I have a video that is specifically about those, that goes into in detail what the differences are. But what OB30 is, it's what's called a cyclic interrupt block. And what I'm doing in this cyclic interrupt block is calling these functions puts and gets. And a cyclic interrupt, I have this one set, I think, for 75 milliseconds. Let's see. And there's a reason, so it's 100 milliseconds. So I spaced it out because I was having some issues with some of my watchdog timers getting synced up and then missing watchdogs, even though they were communicating. But you don't need to know any of that. Not right now. But so what we've got here is, what we're doing is every 100 milliseconds, this block is going to interrupt our main OB1. So, and this goes into kind of a thought, if you're not very familiar with Siemens PLCs, of like, how do you actually organize your data? And I've kind of been thinking a little bit over the past kind of like, I don't know, a few weeks or whatever, that in a lot of motion control systems, everything is broken up into these kind of like operational units. And so you're defining when things are going to fire. And most PLC programs I've noticed don't really do that, even though, or at least most PLC programs that I have written don't follow that same concept. And I've got to thinking about like whether or not that actually should be the good thing or should be the way that I'm doing it. And here's what I mean. Uh, Welcome from some Sao Paulo. Welcome from Brazil. I love the international audience here. If you're first time on the stream, be sure to drop in and chat. If it's not your first time on the stream, be sure to drop a hey in the chat where you're from. We've got people from all over the world on these streams, and it's awesome. I love it. So talking about the way that my OB1, I basically would come in and call my function blocks for my different code. So I'm breaking up my code into logical function blocks, but for the most part, they're just running in OB1. And I got to thinking that motion control systems don't do that. That's what these different don't have it in here, but you'll have a MC servo, which is your servo cycle time. That's an interrupt block. It interrupts and does things, and that's how motion controllers work. And I started to think about it of like, what should actually go into OB1? Like, and so that would be interested if y'all are in here, and kind of some of my more Siemens veterans people in here. I'd be interested to hear your comments and your chats about how you organize your OB1. Do you use more cyclic interrupts, or do you kind of do like I've done here, and for the most part have function blocks and function calls being called in FB1? So I'd be interested to hear that. So y'all drop that in chat. We'll talk about it. I'll show you what I've got going on here. In my OB1, I've got my basic logic of checking signals and things like that, and updating drive telegrams, things like that. These aren't really motion control system. They're just this local drive gets updated with its set point, and if it's off by a few hundred milliseconds, it doesn't really matter. But then I have this remote update cyclic block. And so every 100 milliseconds, this comes into this block. And what it does is, the first thing it does is we'll go in and because these are 1200 processors, I'm trying to be as easy as possible on the processor. And so I am creating this kind of phasing logic. So as it goes in, it does one update every cycle. And so for a 6-pump system, you're getting the full system is updated. LC 27. Do you see my booleans as zeros? You don't see booleans as zeros in here. Where do you see a boolean as a 0 or 1? It's not happening. Not happening. It's a true. Oh, 35 minutes behind. So in 35 minutes, when I see this chat, you'll see my comment. But welcome to the stream, LFC. 35 minutes in the future. So what I'm doing is I'm going in every 100 milliseconds and doing a put and get out to one of these 1200s, just so that my processor load is distributed appropriately. And that is because I didn't want to overload my main function to kind of stretch out. Yeah, so OG is responding to my question. Now he says, so only for critical motion control do I use OB30 or some calculation like encoderless length calculation for motor speed. uh, good to use OB30 or S is in main. Yeah, I mean that's very similar to how I do it. You could see here I have a cyclic PID block that I use it to set my PID update for the local control. And then I'm doing this kind of, and then that way I can just go into one place into the parameterization of that block and set those and tune those update rates. And I guess one of the things that I brought up this kind of thought was the fact that like on my winder system, you have your safety blocks that are kind of running on their cycle. You have your MC servo blocks that are running on their cycle, and then you have your main cycle. And on that one, I have PIDs and all of that other stuff. But I have technically my set points, my calculations, like my length calculations, like all of those things are being set in OB1. And it just got me kind of thinking of like, is that the best way to do it? And so should I be calculating my roll length set point in another block, or does it really matter if I'm off by 40 milliseconds, if I miss a servo cycle or something like that, and it gets updated? Like, and so far our winders work really well in that. But I'm sure that there's some applications, because like Sumotion, for example, Ali Reza is always asking for me to do Sumotion. And Sumotion, when you're in it, most of your logic is not in a just kind of like OB1, the version of OB1. It ends up being in these different motion tasks, which are not they're all cyclic. And so you have this, here's a motion task, it does all this stuff, it does all this stuff, it does all this stuff, and then it does it. And you have to align your motion tasks in order to make sure that you don't overrun your kind of servo cycle. So anyway, just thought of that. So we'll still keep talking about it, but here's how I've done it. And so let's go in and talk about these puts and gets. Looks like a FPGA. What could you explain further, Ali Reza, on that? Because I know what you mean by an FPGA. I guess you're talking about like kind of the parallel logic blocks, and so kind of breaking your logic up into kind of almost deterministic blocks. Is that what you mean by FPGA, Ali Reza? Oh, wait on him. I'm going to pull up. Explain a little bit. So these pump houses, pump house 5 is what this multitasking Sumotion D. Yeah, I got you. Yeah, Ali Reza, that's I see. Yeah, and that's kind of this whole thought process came back from when you start working with Siemens a lot. Everything comes down to, or you start thinking about efficiency more and more and more. And I don't know, that's why I love Siemens, is because it gives you the ability to kind of do all of these things very efficiently. And there's 20 different ways you can do it. Whereas on some other unnamed manufacturer, there might be only one way to do it. And if that, like sometimes some manufacturers don't even have the ability to do some things. And so, yeah, with that said, I've got in my every 100 milliseconds this remote update block coming through, and it's coming through and it will run one put and one get cycle every 100 milliseconds, which you sound like it's pretty slow, but like these set points aren't changing. They're on a PID that's locally fast. So the PID locally is running quickly. So let's talk about this put and this get. So what a put does is it takes data and puts that data into a remote device at a pointer. So a pointer, you can kind of mentioned it before in indirect addressing. A pointer is in the physical memory of the device. And again, I go into a lot more depth and look up the live stream about indirect addressing if you're not familiar with this. But a pointer takes and says, hey, start at this place in memory and then put this data there. And that's what the put is. The get is just the opposite. It says, hey, start at this place in memory on the remote device, on the partner connection, and then pull that out and put it into a data block. And so the way this put function works, and sorry for using the word put when I was talking about the get, but so you're taking your data and putting it into the remote device. Getting the get, you are taking and grabbing that data and getting it into your system. So that's the way that these work. And they basically have the exact same interface. You have a connection ID, you have an address, which is a pointer, and then you have your data block. So your data, either source or where the data is going. And where the data is going to be. Oh my goodness, itching. The pollen has got my allergies all over the place. The southern U.S. is terrible in the spring and going into the summer about pollen. You go through and the cars, every car is yellow. It doesn't matter what paint job you have on your car, you have a yellow paint job. So let's talk about these what is represented in this this data structure. So this here is a pointer. Cue into it. You can see it. The fact that there is if I could zoom in a little bit, make it a little bit easier to see. There we go. Could be a little better, right? So as you can see here, there is a pointer hashtag. So that pointer defines an area of memory. Okay. So a pointer says, I'm going to start here and go down a certain number of places. Okay. So in this instance, what I have organized is on my remote system. Remember this station data here? This is, again, look, it says PH5. So this is the PLC for the PH5. So that's a remote pump. The master pump is on PH4, pump house 4. The pump house 5 has this station data block, and that's it. And then it has its the pump function running, the pump function block that uses this data. So in it, the remote station, the master data from the master system, kind of that control data, starts at this offset 0. Okay. And so what I'm doing is I want to put that data starting at 0. I want to put all of the data in my data type. So what I have done is I know that on all of my remote station PLCs, they're basically going to be exactly the same. I mean, same addresses, same data block numbers, same everything. And that way I can set this block up to where it's not confusing. So I look at this thing and I say, it's DB1. And if we look at the station data, that's DB1 as station data DB1 up at the top here. And start at DBX0.0. And the reason it's DBX0.0 is because that first bit is it's a bit. So the first actual referenced value is a bit. Sometimes you can use a DBW here, but if you use DBX0.0, you're always going to cover yourself. So it starts at 0.0, and then it is putting 34 bytes. So it's putting 34 bytes to DB1 starting at offset 0.0. And we look at what this does just real quick. It's going to come in here, and we see that it's going to put 34. Remember, the first byte starts at 0, so 34 goes all the way down, and it's going to put all of this data here. Whoops. It's going to put all of this data, all 34 bytes of that data, into DB1 starting at this offset. Cool, right? So that's pretty straightforward. So that put address there is pretty simple. Byte 34, DBX 0.0, and now on our end, where are we putting that data? On the local PLC. So where I have it is, I'm taking that, so, all right. So this is a little difficult for this, but because my master pump system generates all of this data based on that local station, because I wanted every single pump being controlled exactly the same, even the one at the pump house 4. So I have this 6-stage pump control that generates that the instance data block is DB20, and so I have this master pump control IDB, and it has a oh, sorry, this is the wrong one. It's master system control, this one. So this master system control is the instance data block. If I go to this OB1 here, for the automated system control. Okay, so in DB20, I have this guy right here, which is the master system data, and so that is that 34 bytes of data that I'm wanting to send to every other remote station. That's it. It generates that one set of data and sends it out to everyone. Well, here, not there. All right. So we're going to look at this system data. Click on this. Yes, OG, there are actually 6 1200 PLCs in this system. I'll show you real quick on the device networks real quick. So this is our system. So we have 6 pump houses, and all of so there actually will be an IM 155-6 in these, just to expand out. But the reason why we didn't just use a remote rack is because we wanted them to have independent local control. So you have to have a PLC control at the local station no matter what. So if the connection goes down, they still want to be able to physically go out there and have somebody and using a radio and be able to control these without with zero communication. So that's why there's multiple PLCs, and then that way they could also take this pump house, hook it up into somewhere else, and then still run the pump. So it's just allowing for flexibility in the system. That's why we have those. So the more coffee, a little water. So I learned from one of my friends who's a musician, that caffeine creates apparently like film in your throat. So you have to drink water to flush out the film. That's why at some point, if this stream goes pretty long, I will have to pee. So that so what we are doing on this put is we kind of understand, hopefully you understand the pointer side of it. Now, my data, my instance data block here, DB20, you could see it hovered, has this master system data in it. Let's just open this this DB20 up. So if you're familiar with instance data blocks, you have inputs, outputs, all sorts of stuff. Well, inside is there's static memory, and there's this master system data, which is a 34 byte structure. And it's the same structure that is in all of these, the same structure that's in all of these different PLCs. So, because it is this pump remote master data type. And so that is that data type that is getting, the same data type is getting used on all of these PLCs. So they're all sharing the same data. So, which by the way, I'm using a library functions for this. And so if I make a change on this data type, all I do is say update all types in library, and it, or in project, and it goes through, and everywhere that data type is used in the project, it updates that, because otherwise it can be a nightmare keeping up to date with different versions. So, so I've got this DB20, and starting at DBX40, so look at this master system here, where this starts is at DBX40. So if I were to go in and change the master system control interface, I would have to update this data, or update this pointer, because if I were to add in an in and out or an input, it would shove this offset down. And so you could see this structure here over on this, in the details view, you can see that if I were to add something in up above here, that if you notice the reset, so like all of the Booleans here, all of the Booleans, it starts at 2.0. And I do that automatically, and I just realized that like Siemens gives you a word anyway. It says, hey, we're going to give you all of your Booleans. So if you structure your inputs, put all of your Booleans up at the very top of your inputs. And then if you go in and add in Booleans in there, it's going to be, you're not going to be having to like keep up with your bytes and everything. So with all that said, this master system data starts at offset 40. It is 34 bytes. So we want to look and say, we're going to take the data from DB20 DBX40.0. Now, this here, you have to generate that pointer by yourself manually. I'll show you on this, because I have defined this. I can sit and take from here, I can just drag this over and drop this in here, and it gives you all of that data automatically. So, but this up here, this pointer, there's nothing to drag into it. So you have to know how to point that, because it's using, you have to know that this data that you're trying to put in there is 34 bytes long. You have to know where it's pointed to. Now, let's look at the get. So the get is the same structure. You're just taking and grabbing data from a remote data block and grabbing it and getting it into your PLC. So the pointer is pointing at the remote station, and it's saying, hey, start there, define an area, and then take that area and put it into my local data block. Okay, my local memory area. And so the way I've done this is, notice this structure. It's still DB1, but the offset, it starts at DBX34.0, because in my in my data here, it is 34 where the local data starts. So that offset is 34. The local data starts because I have 1 dB with my master data and my local data, and they are in the same data block, dB1. But my local data starts at offset 34.0. So that is why this here is dbx 34.0. Now, I have the local data is bigger than the master data. And so it is 46 bytes long. And one easy way to kind of do this is take and look. I mean, if I were to change this, so subtract these two numbers, which is hopefully 30, right? So, no, sorry, it's 40. So we look at this. Let's go back to this. So you're really looking at this last one. And so 84 minus 34. 84 minus 34 is 50. And then your last value is real. So you subtract off 4, right? And that's going to be 46. Is that right? Yes, it is. So, and the reason you're doing that is because this is so this last value here is at 84, but that technically goes all the way up to, it consumes 84, 85, 86, 87. And so that's where it's going all the way up to 87. So that's how you get that offset. It's the length of this. Now, an easy way that you could do this is just go through and change this to, and I'm going to undo this immediately because this is my actual program. But if I wanted to change this to local data and then recompile this, I don't think I have that offset right. I need to update that because I've apparently changed this to where it does. That's not going to work. That's not pulling enough data. Good catch, chat. So what I did was I just put in local data here, and the next available address is going to be the length of that data, and it's 54. So I need to update that because apparently I've gone through and changed that. So I wasn't actually pulling in enough data. So let's do this again. My music went out. So yeah, so glad I did that because that would have been interesting. What would I have missed? Let's see what I would have missed. Why those numbers are different. So in my local data, so I would have missed these values down here. I would have missed from 40. It's probably because I probably added in some set points in here and didn't think. So I need to go through and I'm just going to make a note here. So I will add a note for me to do that. I'm not going to go through and do that now, but that is how this block uses. And so what I'm doing here is each individual station, when I pull that data from the remote and put it in, I have a data block that has a pump 3 local data. And yeah, I should have seen that, because I mean that offset for this local data is 50 plus 4, so 54. And anyway, so that's how you use that Git. Now the last thing that I wanted to show you is what this ID function is. And if you have questions and you're caught up in your live, be sure to ask them, and we'll try to go through them. And if you're getting to this point and you want them asked, and you're a little behind, then feel free to go ahead and drop it in chat, or if you're watching this on demand, drop it in as a comment and I will get to it. Also, the best way to kind of interact after is to join the Discord community, or I guess the Discord channel server, Discord server. That's what it is. It's a Discord server. And yeah, everybody can kind of chat back and forth real time. We've got a couple of different channels in there that will help you out. So be sure to look that up. And again, unfortunately, this code will not be available in the member area, because this is an actual system that will be out in the field. But I just wanted to show you some real pointers and everything, even though I have this one messed up. And I guess the reason why I never did that is because that data, I have not used that, the high pressure warning, high flow warning, low pressure warning, low flow warning. So the Discord is in the chat or the description. Let me grab you that Discord link. Yeah, here you go. There you go. So there's a link to the Discord. But yeah, so the reason why I didn't see this is because I probably am. I know I'm not using these warnings in my code. I have them right now on like some of the HMI screens, and so like they just wouldn't be getting passed back and forth and being updated. So like yeah, there's that. So let's move to the next thing on this, because that is the put and get functionality. Let's talk about this. Let's talk about the ID, because where this ID is, obviously it is a hexadecimal, word-based hexadecimal number. Okay. So you have to use this kind of W pound, 16 pound number. What is this number? That is the connection ID for the local connection. So this is this PLC that's doing the puts and gets, and in this case, it's always going to be this this PH4, the master system, is doing this extra little load. But let's go to the device and network screen. Look at this, and if you pull over, there's kind of hidden over on the side a lot of the times. There's this kind of window that's here. It might look like this. If you extend this all the way out, and up at the kind of tabs here, there's these network overview and connections tab. So what you will want to do is to you will have these local connections here. So for here, you have this local endpoint is a PLC PH4. The partner is PLC PH5. Okay. The local ID is shown here. Now here's how you actually configure those connections. this is where all of them are. And so you can kind of know this local ID, since this is on PH4, the local endpoint. All of these are going to be 100. For this connection, it's going to be 101, 102, 103, 104. Cool, right? Let's go through and let's just check and see if all of these are actually right. So for the local ID for this connection is 100, so it's 100, 100. So the next one out to PH6 should be 101, 101, and it is. PH7, let's expand that all the way out. PH7 is going to be 102, 102, yeah. 103, 103 for PH8, PH9, 104, 104. So, so the 1212C price in the US is on the order of about $300, if I remember correctly. It's a little, it's like $280, if I remember correctly. I mean, we can look. That's a pretty good question. We can go here. Let me get a window and we can look at it. That is a good question. Log that in. Let's see. Automation. Automation systems. Industrial automation system. Controllers. Basic controllers. S7 1200. CPU. Standard CPUs. CPU 1212C. And they should all be basically about the same. Yeah, so 385. And then I know my general multiplier that I get. So this is list price. So normally you get some sort of discount off a list. At least in the US. But let's see. What would that be here? Roughly. Yeah, it's going to be about $270 or so. So that's for the 1212. See? Right. So, and again, the 1212 is kind of on the lower end, but one of the things that I kind of mentioned before, or mentioned a second ago, was the fact that, yeah, the turkey, yeah, that's about right. I mean, most of the time for the prices in the US, so Siemens is kind of we have distributors, so we have Siemens AG, and then we have our Siemens distributor. Sorry, we have Siemens AG, then we have Siemens USA, and then we have Siemens distributor, and then I get my cost from the distributor. And so I know my multiplier comes from a Siemens distributor. Well, technically there's two companies in between Siemens and me doing that. So, and there's also the euro conversion. If it changes, they call that the L1 to L2 multiplier. That's between Siemens USA and Siemens Europe, Siemens Turkey, Siemens whatever. And so those multipliers are set once a year. And so if the price of the dollar versus the euro goes up and down, the relative pricing for components in the US changes. And so when I was working for a distributor, sometimes like these big Italian OEMs would have really good pricing directly from Siemens, and all of a sudden the euro would be dropping. So if the euro dropped versus the dollar, that S1 price basically made made it to where Italians could buy like from Siemens and then ship it over, and for much less than like even the distributors were getting. And so yeah, the pricing can definitely be interesting. So the tax is, there is a VAT, the value added tax, which is built into that that distribution, or the two what's it called? You have your value added tax that's added into that link, but then there is also a if the product is made in China, so if it is actually produced in China and it is not, there's not a middle person between the company producing it and the end user, then the US has to suffer a 25% tax, so a 25% tariff just on top of that, just for it to come if it's produced in China. So that's political stuff as well. That, yeah. The thing about it though is, even with all of that, Allen Bradley hardware, comparably priced, Allen Bradley hardware will be like much more on most of the things, just because of pricing shenanigans. But yeah, the cars, so the German cars thing in the US are more expensive, and that there are some import taxes and things that definitely do come into play there. That's why the county where my my company, Alpha Industrial Technologies, is located, there is actually the only Mercedes-Benz plant in the US is actually located in that county. And they make the all of the SUVs, some of the USA spec cars, and like the crossovers. And then they make the EQS. They make the Maybach. What's the big GL Maybach, like the Maybach SUV? They make that in Tuscaloosa. And so yeah, there's all sorts of pricing shenanigans. But sorry, I've got distracted. Good job OG, for getting me distracted. I feel like that's a goal for some of you guys. Yeah, let's get back to these kind of puts and gets, and let's move on to what data records are, because I wanted to kind of talk about taking this same general concept, and I want to pull up a different program, because I want to show you guys a project. Let's do this one. And again, unfortunately for the members for this one, not going to be able to put these full featured things up, or the full programs, because these are customer programs. But hey, you get to see what's actually there. What I wanted to talk to you about was data records. And for this, I wanted to show you a little bit of a block that I built for a Balluff stack light. And yeah, it can get a little bit of a little complicated on it, but if you're not, I don't think I have one of these stack lights here to show you guys, but let's see which one I'm using. Yeah, I may not be able to use this one then, because this is the LIO link. This isn't going to be a good one, because it's using the read records in here. So I'll use this to kind of talk to you about like data records in general, and then we'll kind of talk about the heart specific kind of data records. because data records are, you have two kind of memory areas inside of a of an address. You have what's called the cyclic data, and then you have the acyclic data. And in this case, we have, I'll show you what this system looks like. It's a bit of a weighty system. Close this out. It's got a couple of nodes. So that's a cooler, dryer. Where is my processing? There it is. So what I have here is, we're going to go to the device view on this. What I have here is an IO link setup, and I have on it, one of them is the so this is a condition monitoring sensor, and so it has input data only. And actually, I can't remember which one this is. Yeah, it's this one's it, the 32 byte. So the 4 byte is, it has a little bit of input data, and then it has mostly output data. But what this does is it is actually communicating to a Balluff programmable stack light, and it's pretty stinking cool stack light. And if you haven't seen those, I'll probably link in the description or somewhere to a video of these stack lights, because they're fully RGB LEDs, and you can program each level RGB LED, and you could do levels, and like, it's super cool. I'm using this to actually, so if you were walking in where this pellet mill is, you can actually see the loading on the pellet mill on this stack light. So it has a level indicator on the stack light as it's going through, of like, hey, this pellet mill is loaded, this pellet mill is overloaded, it'll be red, it's underloaded, it'll be yellow, and so it'll kind of be going through. Well, the way this works is through this stack light block, but it has to send out a port and a record. So the data record that it's wanting to send, it is trying to send out through the IO link into these data records and pull that data record back. And inside this device, and I will, for you guys, I will put in the member areas, I will put these stack-like SDU setups and stack-like control, so this ISDU setup is how it programs this device. And this internal block, so it's a couple of different blocks, uses this LIO link block that is from Siemens, and it is using these data record things. And so I will put this in the member area block, but basically what this does is this sets up the stack light, so you get to you can program the different colors for different segments. I have this to where it's wanting to do a level, and there's a level type. The number of segments is going to be 4. The level resolution is going to be 4, so it uses all 4 of those. And it's setting this thing up for that level control for the Balluff stack light. And it is not extremely simple, but this block sets up that Balluff stack light to do the level control. And I'll pull up here in a second. Well, I'll also include the manual in the member areas as well for this. But what this does is, obviously, all of this data is not in those just couple of words that are getting sent back and forth acyclically. It is sending these data records down this kind of hidden communication path, this acyclic communication path. And it sends it out, it gets a response back, and then that's how you modify and change these data records. And so that's how you set this thing up. And inside of here, this actual PM Stacklight control block, I'll show you how it actually goes through here. I have this interface to where it says, hey, activate the alarm. Here's my level that's coming in, all sorts of stuff. So let's go and look at this block in the actual program where it is. Let's see if we can find it. I want to say it's in zone control. It's been a minute. Zone 350 maybe. All right, that's power wheel. Here it is. Backlight control. So what this does is it takes in the hardware ID of that Stacklight communication and the master port from the actual IO link device. And so it's packaging up everything, and you send it, hey, here's the pellet mill current, but you can obviously modify these blocks and these kind of tags, but it's looking at that level, setting this up as a level. And yeah, and so, but this is using data records. And so let me pull up, let me go through, and I'm going to be a little bit of a break from the screen because I need to go through and find, I'm going to need to find this, the block that I was wanting to show you guys. If you have any experience with these data records, you know that they are all kind of in function blocks that are not in function blocks. They are in, what's it called? The manuals. And I thought I had this manual pulled up, but I guess I didn't. And so I'm having to find it real quick. Let me find this. Take a little bit of a break, but right. So I guess we'll go back here. And we are talking specifically about this guy. This AI 8 input heart high function manual. Okay. So again, we talked about this before, that heart is, some sensors that are heart compatible will have a extra data that comes into them from the sensor. And so that heart data, you configure that at the sensor of like what to send out over the heart data. And then you're going to pull that data back into the system in some different way. We talked about this before on another stream, but I just wanted to go through on the data records portion of it so you can kind of understand what you're pointing to and what you are kind of pulling back. So one of the things about these data records is that data records have what's called a data record number. And that data record number is kind of a command. It says, hey, device, I want this data. I want this data record. And then that's what comes back. And so in this, if you look at it, this data record number 80, it's heart request channel. It's a 240 byte channel. So heart response 240 bytes. So this is a lot of data because heart is kind of like a generic interface. Well, one of the things that we would be looking at on this is these heart, like 121. So these heart variables, heart parameters. It all depends on what data you are wanting to get. And let's look at, if I remember, Let me look at the. I may need to look at the Discord because we have this in the Discord in this read record discussion. What page is that? Data set 121. This heart variable, structure of a heart variable on page 79. So close. Is it? Sorry about that. 75. Is it 75? Oh, this might not be the same. Oh, it's not. Let's just do this. We're gonna pull this over. So this is what we're working with. And so this is in data set 121. And this is what this means is if you call that heart variable, the data record 121, this is the heart variable data record that you're going to get back. So you say, hey, 121, what's going to come back? Here's all the stuff that's going to come back. Now, your area should, most of the time, if you don't want all of the data in it, you can restrict where you want by that pointer structure. And so that's what we're gonna look at here, because what we're wanting here is this value. Am I blocking? Okay, yeah. So these values up here where they are the channel 0, value, quality code, value, quality code, value, quality code, value, quality code. That's what we're wanting. What's up, Saif? And what's up, Lucid? Y'all snuck in here when I was looking at my other screen. So welcome to the stream, Lucid and Saif, some of our chat veterans. And so we're looking at these data sets. And so let's go in and take a look at an example in this of the data acquisition starter. Is that what I want? Yes, I do. Because here's where I've used this read record function before in this kind of like fairly complex. So this program is for a fertilizer plant, and it's got a lot of different equipment, a lot of different data. And so it's having to go out and pull data from here, pull data from here. And this is for these ET200 SP starters. So in a ET200 remote rack, you can put, it's like a 3RK, I believe, or is it 3RK 19, I think, something like that. But it has some regular data that comes across as tags, like tripped, start, stop, rotation, things like that. Those are built into the tags, but the data sets, in this case, I'm wanting to get the current. I want to actually get the current feedback, and it is in the data set 94, and it is 3 bytes long. And you might be sitting there and it's like, wait a second, 3 bytes, that doesn't really make sense. But we'll say that this read record, what you are doing is you point to your hardware ID of your device. So that connection hardware ID, and I'll show you how to kind of, again, so this is inside a function block, and so everything's hashtag out. So I'll show you show you an example of how this is used. Data collection. I think this is one. Yep. Data acquisition starter. So you give it this hardware ID, which is the hardware ID for whatever component that you're doing. That if your heart, so you would look this up. So this is on remote rack C receiving 100 motor starter. So let's find that, because sometimes this can be a little difficult in a big system. So remote rack C receiving. We're going to click on this. We're going to go to device view. And we're going to find our device. And in a heart variable, you would, this would be like your heart IO card. But in this case, we're going to be doing motor starter 70 here. We're going to click here. And properties. And I believe IO address here, blah, blah, blah. Oh, no. It's here. Sorry. Is it here? Is it? See. Because the way that I actually find this is not by doing this. Oh, system constants. Duh. So you go to your device here and find it in your rack, find the actual device, and if it has a hardware submodule, so it has a communication path, it will, in your system constants in your device view, it'll show up there when you click on it. And so like here's the one for .10 is 525, 26, all of that. The way that I find it is in my thing, because I name everything. I just start typing in RR-C and receiving blah blah blah. I just start typing into it that way. So that's your hardware ID, and then what you need inside of it for your read record. You need your hardware ID, which is getting passed into this block. Because I know specifically for this block, I am wanting 94 for these little in-rack starters, because that's in the manual. And again, in my I have a video that is about read records and write records, and it goes through this exact same block here, and it is kind of go through this as well. I just wanted to kind of go through and talk about it here, is that in reference to our heart variable, we, instead of doing 94, we would be typing in 121. So because we are in data set 121 here, we would type in a 121 on our index. Now, what is this M length? What is the M length? Well, it is going to be the length of data that we are wanting to pull. Okay? And in this case, I'll show you. We are wanting to pull in all of these channel 0 numbers. Okay? So with this pull, it's going to pull the data from the start, and if you want to pull in different channels, you can pull in all of that data in one pull. But for this particular channel, each channel has 4 bytes for a real value. So this value is 4 bytes. Then the quality code is 1 byte. So it's a word. So it's 1 byte. So for each one of these values, you're going to be pulling 4 bytes. Okay? Straightforward. Data set 121, if you want to pull all 4 of these values, 1, 2, 3, 4, you're going to have to pull 4 times 4 bytes. So if we wanted to pull all of channel 1 and only channel 1 with a read record, our read record would be, let's just do this. So we can kind of play around with this. I don't want to mess up my program, but We're gonna not save this. So, our request is going to be Boolean. Our L address is let's see. Not that. Oh, this is the wrong thing. This is the one we're wanting. Yeah, because it actually has a DB. Do that. So here we go. So there's our data. So our ID is our hardware ID that we discussed earlier. So I mean, we could do like whatever. There's an analog input. Cool. Index. If this was a heart analog input, we could do 121. If we wanted all 4 variables from our first channel, so our 4 extra variables, yeah, the variables themselves, the values themselves are 4 bytes each, but then there's that extra word, and this is a continuous block of data. So we take in the 4, we do, so you have 0 through 3, which is 4, and it's 5, right? So 5 bytes times, right? That's going to be, yeah, 0 through 3 is 4 bytes, and so you have 5 bytes, so it's going to be 5 times 4, so it's going to be 20. So our length is 20, and then we're going to need a somewhere that to store this data, okay? And this is where it gets a little tricky. And we talked about this before in last week's stream, but I do want to go through it again. Let's make a data block just called my read rec db. Okay, we're gonna that was a function block, the function block. So let's delete this. Yeah, actually make a data block. My redirect db. That. And so what we're wanting to do, we're wanting to do a value, and then we know that value is a real. We can do now a v1 quality, and this is a word. Okay, so that is the first bit of information that is here on channel 0. We have a value and a quality code. So value is a real value, and then quality code is a word, 1 byte. So now if we want to get the other channels, we're pulling all 20 of these bytes, correct? So we're just going to repeat this over again. Value 2. Let's just do this. And this is real. And I'm going to do it this way because I'm just building a straight data block without using any special data types. Because last week I used some special data types and tried to set something up, and I realized that was a little bit confusing. So v2, and this is a word, and then we just keep going through. So value, remember there's four of these values. Value 3, it's real. V3 quality, it's a word. Now if you notice, this is whatever, a little slow doing this, but whatever, it's fine. Value 4. Yeah, so, oh no, you're totally right. You're totally right, Lucid. Almost messed up. So Lucid just brought in a thrown in a thing that I'm calling a byte a word. This isn't a word. This is a byte. And so Lucid brought up a very excellent point that this wouldn't work because this is actually byte here. Good catch. And then V4. That's a byte. This is real. All right. So we have this data block here that has this structure for these values. So you value one quality, which is a byte. And so, but we don't have our offsets here. See? And we talked about this at the beginning of the stream, that because you don't have the offset, that means that this block must be an optimized block. And remember, if we're going to be using these read records and pointer access, we can't do it that way. It needs to be that way. So we're going to go into this. We're going to properties. We're going to uncheck this optimized block access. We're going to say, yeah, we want to change block access. That's why we're clicking it. We're going to click OK. Now you say, all right, these offsets aren't there. Well, you haven't compiled this block yet. So once you compile it, there you go. Those offsets are there. So now this is ready to use this data record block. So at this point, what we can do is we can actually just, in our little test function here, we should just be able to put that there because that's our record. And so the way this would be doing this is our read record is going to go in and say, I want to read data record 121 on this device. I want to pull 20 bytes. It doesn't really know what that data is. And so you're structuring it in this data block. Okay. And that data block is structured the exact same way that this chart in your HART manual, in the IO record for, or the IO manual for this HART module, that is how that is structured. And that's how you would use this read record. Okay. Now, to take it one step further, to show you, instead of, because the subtle difference between the way that I did it last week and the way this is a data block, standard data types. This 100% would work. I'm going to make a little bit different, and I'm going to show you, I'm going to make the same data block a little bit different. I'm going to show you how they're functionally the same, but, and why you might want to do it. So the first thing that I'm going to do is make a custom data PLC data type. Okay. And I'm going to name this data type. I'm going to name it HART record, or HART value. Okay. And in it, I'm going to make a name value. It's going to be a data type real. And then in this, I'm going to make quality, and I'm going to make it a byte. Okay. Save that. Oh, I wish I hadn't saved that, but whatever. Meant to compile. Before I forget this stuff. Okay, I didn't change anything. I should be in a I didn't want to actually save that. Fortunately, I have an archive of this, so it's no big deal. But so I have my HART value that I just made, and I'm going to make a new a new data block. So compare it. It's a data block, and I'm going to do it by part type DB. Cool. And then now, instead of, so I'm going to say value 1, and now I'm going to do a heart value data type. You're like, okay, why am I doing it this way? Value 2. I'll show you why. Because now I can just go whoop, value 3 and 4, and I have all of these. Okay, so, and what I've done is I've built in that real and byte structure, the same as over here, right? So now I need to go in here, do this properties, uncheck optimize block access, and we're going to compile that. And now I want to float this, and let's look at let's compare these two blocks. Hopefully they're the same. So let's open all of these up, we expand them all out, and you look, the offsets are the same, because all a UDT or a custom PLC data type does is structures kind of bits and bytes. And whereas a real value is just a defined structure of some bits, a custom data type is just a defined structure of other data types. So you look, these are the exact same functionally, the exact same. And so I would be able to go into my test function and get out of here. I would go into my test function here, and then I would be able to do this, and then my heart type DB, exactly the same. And so my read record DB, which is just me manually going in and every single one, just copying the structure in this table, and then me going through and saying, oh, hey, this value quality code, that's one value. Now, if I wanted to, I could go through and in this heart type DB, I could go and even say, go as far, and now I just might be just showing off a little bit, but I want to show you how to add another data type as part 121 channel. Let me spell it right. Channel data. All right. Okay. And I did this in the wrong place. Control X. I meant for this to be out here. Name this. And again, I can't ever go through using data types enough, and so that's why I choose to do this. So so we'll do this value 1. Whoops. Let's do this. And you're like, Jason, what are you doing? You're just copying the structure of this data block. Well, if you look at this, there's actually 8 channels in this, right? So what I'm going to do is I'm going to say value 1 is, and this is just the same structure as before. So value 1, you have a heart value, all of this. So go here, and then now what you can do, this is channel data. And so let's go to our heart DB like this. And instead of doing this, let's delete all of this. Collapse all this. Let's delete everything. And okay. And if we compile this and we expand all of this stuff all the way out, we have the same data there. And you're like, Jason, why did you go through that complexity? Why in the world would you add all of that stuff when I could just type it in? Because of this right here. What if I wanted all 7 channels? 0, 1, 2, 3, 4, 5, 6, 6 elements. Channel 1, 2, 3. Oops, undo. I need to do one more. You do this right here. 7 elements will be added. And you're done. That's why I did it. And now, if I add in another IO card, I could just do the same thing. You could even go as far as to say, take it one step further and make a data type of heart 8 input card and do it this way, and just make it to where all you're doing is you just have multiple card data in one data block. And so now you're just pointing to these little places, right? And the difference between that would be you would have your, in this one, for example, my test function here. So there's 20 per channel, right? And then there's 8 channels. So 8 times 2 is 160 bytes, right? $160. So let's see if that lines up. I'm pretty sure it does, because you've got this channel 0, channel up to 159. Yep, that's right. Then 159 is 1 byte. So this next thing is 160. So let's go through and just check this, and we'll do the compilation. We'll go all the way up, and oh, what did we do? Did we mess something up? Looks like we messed something up, didn't we? This channel 0, so it's 1, 2, 3, 4. That's 4. I don't know if this is right, but you could do this. You could basically keep making these data types and making them kind of one level up. But 20 through, that's 40. I'm off by 1. So channel is 4, 5, 10, 15, 20. And then there's 20 times 8. 2 times 8, 16. What have I done? What have I done? 2 times 8 is 16. So that's 160. So I've messed up something somewhere to where I've got, because I've got 22 here. So why am I off the 0, 4, 22? Because it's adding in extra bytes. Anyway, so that's how you would do this. So the easiest way to kind of like get started is to go through and directly duplicate this structure, right? And maybe I'm just reading this the wrong way. It should be 19, and then channel should be start at 20. So what have we got wrong here? 0, 1, 2, 3. That's value. Then quality code. Real byte, real byte, real byte, real byte. Oh no. 4, 4, 6. That's where it is. I don't know if this is actually right, but anyway. Yeah, so we go through and yeah, the byte is occupying a word. Yeah, the offset is, it's not. You're right. Because that should be starting at 5. That's interesting. Why is it doing that? I might have messed that up when I first typed that in. Because yeah, the offset is right. So for some reason that byte's off occupying a word instead of just a byte, which is weird. Maybe there's something in that, is something that I have not experienced. And so that's probably, that goes back to the problem here is your that byte for some reason is not getting set up correctly. What would I do without you, Lucid? I mean, my stream wouldn't be as good. That's what I would do without you. I'm not sure why it's doing that. Those offsets, that shouldn't be doing that. I'll need to figure out that, but that is what is going on there. But yeah, that's how you use the read record function. It's just for some reason that those bytes just aren't coming in correctly. Let me try something. Could just be something dumb like this. I want to see if for some reason we put in everything as a byte, if it would be fine with it. Which it is. So why does, when we change this to a real, we're experiencing new things? It works fine there. Did we just find a bug, chat? What the heck? Why won't it do that? It won't start a reel on an off address. So that is going to be an issue in reading that record. Yeah, so what's happening, Chad, is and I don't know why this is. Maybe somebody that's smarter than me in chat, if you see this, and like, why is so like a real value can only start on an even byte offset. But like the offsets for the reals have to be even numbers. And so what's happening is if everything's set up as bytes, I can get byte-wise access to it. But if I immediately say that it's a real value, the offset will be it gives me too many bytes. It starts shifting data the further I go down into it. So after that first, so here, what would happen, this real value here needs to be starting on offset 5.0, but it's not. And so this whole heart problem that we were talking about, tension in the Discord, this is what's going on. For some reason, your offset is getting messed up because of this real value here. So what we're going to have to do, and let's see if we can figure out the best way to do this, you would have to set up bytes this way. And so how would we bring this in? I'd have to think about this, because the best way to do this is going to take a conversion block in order to organize this data. And that's a little obnoxious, isn't it? Because you are trying to distract me, Ali Reza. So so tell you what, like, for this tension, if you're watching this later on, like, on demand, I see what your problem is. And so we'll talk about it in the Discord. If you want to follow up with this, be sure to join in the Discord. It's in the chat. I'm ignoring you right now, Ali Reza, but I'm gonna come to you. But if you want to follow up on this problem with the read record and organizing this data, we're gonna follow up with this in the Discord, and I will probably make a YouTube short about this value, or about what we come up with the best way to do this. And honestly, in order to make this worth it, I'll make y'all a block. So I'll make the members a block that does this sort of conversion for these heart values. I would say that would be a pretty good function, wouldn't it? Yeah. So if you find that sort of stuff valuable, membership might be in there, since, again, like I've mentioned before, members aren't going to get access to these full programs because, frankly, they're actual customer programs. So, all right, Ali Reza, you'll be distracted, or I will be distracted. Let's go here, and I'm gonna have to go back through that later and delete all of the stuff. Actually, before I forget, I'm going to delete all of this stuff and try not to delete things that are actually important. And then these PLC data types. So but yeah, so Ali Reza has a question while I'm deleting this in chat. He says, just to distract, do you have a training program for motion control in S7 1500T or SciMotion? What do you mean by training program? I have some stuff that is training material from things that I've gotten from US-based training, but so the way that training material is by taking those classes, I'm not allowed to actually distribute that particular content, or at least in the motion control content. I did a SciMotion kind of like basic training class a while back that included a lot of that stuff. But yeah, I don't know how much of it I actually had with like training material and documents and things like that. I have most of the 1500T stuff, I mean, is kind of what I've done on this channel, and going through step by step the different blocks, the different stuff that we've talked about. Honestly, that is the training material. You could type out, I guess, some of the stuff that you would like to particularly learn about, and put it either in a comment, or I guess you're in the Discord now. We could probably come up with something on it. But yeah, kind of probably the Motion 101 class had a good bit of the 1500T program. Um, but yeah, I'm trying to think of what else out of these things that you would probably kind of get out. Um, but yeah, definitely can do that. Um, but probably Motion 102 is going to have a little bit more of it. And I know you're wanting the Samotion. I know you want the Samotion. I will say a good thing that I guess is coming up. I rented out a lab space. Um, so yeah, Lucid looks up the help file, says that all structured data types are aligned to an even start address. Okay. So anything other than a byte. I'm reading padding bytes when using structured data types. Yeah. So Lucid. So that's something that I need to do for this heart, especially for this heart data, the way it's structured. The fact that it's done that way is a little weird. Is you're going to have kind of an interpolator block that's like taking those padding blocks out and kind of reorganizing it. So basically going in and taking the structure, taking 2 bytes and creating a reel. And you could do that with kind of overlaying tags. Yeah, I would have to come up with a way. So I think that'd be a pretty good value for us to do. Maybe on a casual stream or something. Maybe this weekend. I'm gonna be going up on site again over. I'm heading out tomorrow actually, and I'll be out for at least a week. But maybe I'll be able to do a casual stream or something to where we just build that block, because I think that is a good exercise in data structures and memory. And I don't know if I have that. I'll have that heart thing done yet, but I'll see what I can do. But yeah. As for the motion, Ali Rezo, you'll just have to, like, what are you specifically wanting? For some motion, I could do a basic class setup, and oh, I started talking about this. So a little fun thing that I'll be able to kind of expand what we do on stream. I have leased out a laboratory warehouse that I'm going to be kitting out to actually have 3-phase power and all of these devices to where we can actually run motors. I can do the live streams with real equipment set up in kind of a studio environment, and I can actually go through and do that. And so I'm just getting everything set up. It'll probably be a couple of weeks. I'll be, again, off on the customer site for about another week. But once I get back from that, I'll be back and forth, like going to different customer sites for, I mean, really about the next month and a half, 2 months. But hopefully in about a month or so, I will have a setup to where we can actually do drive, like actual drive training, and I can have like a video stream of the drive, of the motor, of it actually working over on the shelf, and then a split screen of like me doing this or doing the work on it and kind of playing with it. And so once I get that set up, I will probably be able to do a much better job of a training class on Samotion, on 1500T, just because Samotion is fairly straightforward once you get kind of everything going, especially when you're using the motion control charts. And if you're not familiar with Samotion is a Siemens very specific motion control platform, and it has a built-in PLC, a built-in CU320-2, and yeah, it's pretty powerful. It's very powerful, actually. I think it can control like 128 axes for the D430 or 445. I mean, it's really powerful. Um, yeah, so I might, I think I have an older D445 that I might be able to do something with that we could play around with. I've got some motor modules and things that we could set stuff up with, and but I'll have to be getting the lab set up for that. But yeah, I mean, the day has been more of a PLC based day. I know. I will try to get back into a little bit more of the drive based stuff. Um, I've just been busy. It's been kind of crazy. I will actually be probably so in 2 weeks. We'll be here, so we'll be able to do a couple of live streams and stuff. Hopefully in 2 weeks. Then after that, I'll be back at the mine site, and then probably after that, I might have a week. So it's busy. It's fun though. But yeah, this is going to be it for kind of what we are doing today. And yeah, if you've made it this far, thank you so much for kind of everything, all the support that you do. Um, to set that up here in Tuscaloosa. Unfortunately, Lucid, no. That I mean, we have our we have our our shop down south of Tuscaloosa, but the the laboratory that I've rented out is actually here near Georgia Tech. So if you are in the Atlanta area and you want to kind of get involved in some of this stuff, uh, will be setting up a laboratory. It's just on the west side of Georgia Tech, actually. So hopefully we'll be able to get more people involved and maybe bring in some students and kind of that's kind of the goal because this channel, my goal is to be able to reach as many people as possible to be able to, yeah, to be able to get people involved in automation. And that is kind of what we're doing or what I'm trying to do there with that. And also develop some cool stuff and kind of do all of my side stuff as well. Do like cosplay and animatronics and all of these other things that I never shows up on the stream, but I spend a lot of time doing uh, that will kind of be going out of there as well. So just a lot of fun stuff. But yeah, that's all in the Atlanta area. And yeah, again, I appreciate everybody that is always on these streams. We've got the familiar faces, the blue stars, the the named people that every time that's always in chat commenting. We appreciate y'all so much. Even if you're just liking and subscribing, that gets this channel out there so much more because the more you like a channel, the more the YouTube algorithm says, "Hey, this is valuable enough to put it in front of other people." And yeah, sure, this is not the most entertaining content. It's definitely not a Mr. Beast video, but for people like us that are looking to kind of improve our professional lives, improve just kind of where we're going through our life, this content hopefully is valuable to you. And there's so many different ways that you can get involved. Liking, subscribing to the channel is actually a great way to do it. If you want to get involved in the discussion offline, the Discord link is in the channel. And if you're wanting to get these kind of data blocks and the functions that we make on stream, again, I can't repeat it again. You won't be able to get the programs that we were working in today, but normally the data types and things that we make and we do on stream, I make available to members at different levels. And so um, those programs at the membership level of the programmer level, you get to actually get those programs. Not those today, but normally you get the program so you can play around, have that structure that you can kind of mess around with and see what we do. But yeah, that's going to be it for today. I appreciate everyone that has joined live if you're catching this on demand. And yeah, just thank you so much for your support. Next stream will probably be maybe I can get one just kind of a casual stream sometime during the week. It all depends on how well the hotel internet is. But yeah, so glad that you've joined this time. And again, if you are new to this channel, look around and watch some of the videos. Hopefully, it will help you in your automation journey. Until the next stream or the next video, keep learning and always be humble. Take it easy. Bye.